Hi everyone. So in these few videos, we will be looking at the Jacobian matrix for a robotic system and a few methods that we can use to calculate it. So the Jacobian matrix, or a Jacobian for short, is used in a variety of fields in mathematics and physics, but here in robotics, we will use it mainly to find singularities, the forces and torques that can act on a joint, and the joint velocities. Now this topic has a reasonable amount of calculations and some parts can be confusing or difficult to understand, but I will do my best to simplify it down for you. Without waiting any longer, let's get into it. So if you guys like this video, don't forget to give me a thumbs up by clicking the like button below. And if you haven't done so already, go ahead and click that subscribe button right now. I'm Chums and welcome to ThatsEngineering. Alright, so the Jacobian matrix. The first thing you should know is that it is a multi-dimensional matrix, meaning it can have multiple rows, multiple columns, and it would be made up of the derivatives. So practically the Jacobian is all about the velocity. The Jacobian matrix would be made up of the equations or the velocity vectors. But when we do a question or a calculation, the easiest thing to find would be the position of the joints and the links. But by taking the differentiation or the derivative of this position, we can find the velocity and thus the Jacobian matrix. So what you should know is that the minute someone talks about the Jacobian, they're referring to the velocity of the joints in the system. Let me give you an example. This can be generalized for almost any robot or any system involving the Jacobian. You can have a general set of equations that describe the position of the system, such as y1 equals f1 some function with variables x1, x2, and so on. y2 would be f2, and you can have multiple equations depending on the size of the system, which would represent the position of the joints or the links in this robot. When you take the differentiation or the derivative, and here you will be doing partial differentiation because you have multiple variables in the function, you would get something that looks like dabba y equals dabba f over dabba x times dabba x. And this would actually be a matrix containing y1 dot, y2 dot, and so on, followed by the matrix holding the derivatives of the function times the matrix holding x1 dot, x2 dot, and so on. So this derivative of the function would correspond to this matrix, and that matrix would be the Jacobian. Now I'm not going to go into detail on this because we will have a look at it again when we are doing partial differentiation in my next video. So let's keep this aside for now. Right, and let's have a look at the definition of the Jacobian. So the Jacobian can be used to relate the joint velocities to the Cartesian velocities in a robot manipulator. So let me show you this in an equation format so it would be easy for you to understand. A joint or a link, usually a joint for a robot, can have a velocity, and this velocity can be expressed in terms of the position vector for the three coordinates x, y, z, the derivative of those position vectors, and this would be the velocity in the Cartesian space. This would also be equal to the velocity in the joint space, which would comprise of two values, and this would be joint space where v0 would be the linear velocity and omega would be the angular velocity or the rotational velocity. And this would actually be equal to the Jacobian times whatever variables are there in the system. I'm taking θ1 and θ2 for example, the derivatives of that. So the Jacobian can be used to relate the joint velocities to the Cartesian velocities. Right, so before we move on to the next topic, there's one more thing I would like to discuss, and that is the frame the Jacobian is in. Now, just imagine a simple robot, sort of something like this, with the 0th joint or the base frame being 0, this being the first frame, first joint, second joint, and the third frame for the tool. To perform most of the calculations involving torques, forces, and singularities, you would need the Jacobian in the base frame, or J0. But when performing the calculations to find the Jacobian, you may end up with the Jacobian in the final frame, J3. That being said, you can also express the Jacobian in any of the other frames as well. And from these other frames, we would need to use that value to find the Jacobian in the base frame. So how do you do that? Well, it's actually quite simple. The Jacobian in the base frame is equal to the rotation matrix from the base to any frame, I'm using 3 here as an example, times the Jacobian in that particular frame. Right. So you have to remember this equation. Practically, what you have to know is that if you have a Jacobian in a higher frame, simply multiply it by its rotation matrix, which comes from the transformation matrix. So you have your position, rotation. So you multiply it by the rotation matrix to get the Jacobian in the base frame. Alright, so now let's have a look at singularities. I'm not going to go into depth on this topic, but I will give you a brief introduction. By definition, a singularity is a point where the robot loses one or more degrees of freedom. And at this point, it would be impossible to move the tool of the robot in a particular direction, regardless of the joint rates. Now, there are two main types of singularities: workspace boundary and workspace interior. If you're not quite familiar with the term workspace, practically it means the area that the robot can operate in. So if this is the tool of the robot, it can operate within this entire area and reach any object within this area. So that would be the workspace of the robot. So for workspace boundary singularities, there are two cases. The first one being that the robot can either be fully stretched out or folded back on itself. And for both of these conditions, the tool of the robot would be at the boundary of the workspace. In workspace interior singularities, the tool is no longer at the boundary, but two or more joint axes would line up with each other. For this particular type of singularity to take place. So, alright, so to help you visualize singularities, let's just take this example of a very simple robot with 3 joints, and this joint can be rotated by an angle theta. Now let's say we rotated this robot, or rotated that joint, such that the robot was in a straight line. Here theta would be equal to 180 degrees. And at this point the robot has lost some degrees of freedom, and therefore it is at a singularity. So the value theta equals 180 degrees would be the point at which the robot reaches its singularity. And it would be of interest to calculate singularities, because we would know at what points the robot loses its degrees of freedom. So we can program it to not reach those particular angles, or to not allow the joints to rotate those particular angles, to stop it from getting stuck, for example. Right. So to calculate or to find a singularity, you will look at the determinant of the Jacobian. So if the determinant of the Jacobian is equal to 0, then a singularity or singularities would exist for the robot. If, however, the determinant of the Jacobian is not equal to 0, there would be no singularities for that robot system. Right. So these are two things that you have to keep in mind. Now, when performing calculations, if the question asks you to find the singularity of a robot system, then you would find the determinant of the Jacobian and equate it to 0. And you would get an equation with multiple different variables such as theta 1, theta 2, and so on. And by equating this whole equation to 0, you would be able to calculate some values for theta 1, theta 2, or whatever the variables are there. And those values, so just for example, let's say theta 1 is 30 degrees, theta 2 is 60 degrees. These values would be the singularities. So you would not want the robot or the joints to reach these particular angles. Alright, so now let's have a look at the two methods that we will use to find the Jacobian. I'm not going to do any examples or explain this method in detail, rather just an introduction to each method, and I will go through each method separately in the following videos. So before we do that, just keep in mind that the Jacobian involves finding the velocity of the joints and the links of the robot. Right, so the first method is the partial differentiation method. So let's start from the very beginning. You have a robot, you assign your frames, you analyze the system, and you're able to form a DH table. And from this DH table, you would be able to get your transformation matrices. So you would have something like T01, T12, and so on. And using these transformation matrices, you can calculate the transformation matrix from 0 to the tool or the end effector by multiplying all the previous transformation matrices together. 1 to 2, and so on until you have n to e. And this final transformation matrix would be in the form of a 4x4 matrix with a position vector and a rotation matrix. So this position vector here would comprise of three values. You would have a position in x, y, and z. So this would be the position of your end effector relative to your base frame. And if you were to differentiate each of these three and combine it to a matrix, you would have px dot, py dot, and pz dot. and the equations that you get can be factorized into the form of the Jacobian relative to the base frame and whatever the variables were there in the equations. For example, theta 1, theta 2, and theta 3. So in this case, you can directly calculate the Jacobian in the base frame. Now let's have a look at the velocity propagation method. So in the velocity propagation method, you would first need to find the linear velocity, denoted by v. And then you would need to calculate the angular velocity, denoted by omega, keeping in mind that some people or some textbooks would use this to denote the angular velocity, this symbol. And there are already equations that you can use straight away to calculate the linear and angular velocity. You do not really have to take any derivatives or do any sort of differentiation. As the name suggests, velocity propagation method, you start from the first frame or the 0th frame and work your way up frame by frame until you reach the final frame or the tool frame. So here you would finally have the velocity in the tool frame, and that velocity would be equal to the Jacobian in the tool frame times whatever variables you had in your system. So from this, we can calculate the Jacobian in the base frame using the rotation matrix from the base frame to the tool frame times the Jacobian in the tool frame. Alright guys, so the final thing we're going to look at in this video would be torques and forces. So we have two main types of joints that we looked at in this course. We had revolute joints and prismatic joints. So a revolute joint would actually produce a rotation, and so there would be a torque, while a prismatic joint would produce some sort of force. So for example, we had a system like this, with two revolute joints and one prismatic joint. You would have two torques in this system, tau 1 and tau 2. I'll better use a different color. Tau 1, tau 2, and a force from the prismatic joint, F3. So you can relate the forces and the torques to each other by using a Jacobian. And that is done using this general equation is equal to the Jacobian from the base frame, the transpose of that Jacobian times F. So what you would actually get from this is related to this particular robot system. You would have tau 1, torque 2, and F3 equal to the Jacobian of that system in the base frame, the transpose of that, times the three unit vectors fx, fy, and fz. Alright guys, so I will have 3 more videos on the Jacobian matrix. The first video will talk about partial differentiation method, the second the velocity propagation method, and the third video about torques and forces. So this video was just an introduction to the Jacobian matrix, but we will get into the examples and the calculations in the coming videos. Right, so that's all for this video. If you guys like this video, don't forget to give me a thumbs up by clicking the like button below. If you have any questions or clarifications on the work we just did involving an introduction to the Jacobian matrix, please feel free to leave a comment and I will do my best to get back to you. I hope this video helped you, and if you haven't done so already, please hit that subscribe button right now. Thank you for watching, and I'll see you all in the next video. Cheers.